Okay, so this is now the lecture on week 6, day 2, discussing capacitors current in the newer discussion, where we're now going into leaving the whole topic about the static case of electric charges, but we're considering now moving charges per time. I first actually want to go back and consider this as sort of as a review for the midterm exam next week. I first want to make a few brief remarks about the electrical potential energy U and versus the electrical potential V. And then, as I did actually during the last class, remind you what a capacitor really means, namely an arrangement, a general arrangement of two metallic objects, both of which carrying an opposite charge, one a positive charge of magnitude q, the other one a negative charge of magnitude q, in a certain geometrical configuration, be it planar, for example, cylindrical or spherical. There's an electrical field set up between both. And the ratio of the actual charge divided by the potential difference between these two objects is a constant characterizing that geometrical configuration, and this is called a capacitance. So we'll go through this today, and then at the end we'll start a new topic where we're, as I said before, where we're then leaving the notion of charges at rest, now considering then charge moving versus time. We come then to the notion of defining current. Current flowing, for example, charges flowing through a metallic material, but they're experiencing a resistance because there's other stuff around inside of a metallic material, and we're defining a quantity which is referred to quantify that amount of resistance, called resistance. All right, let me first remind you now of the definition of the electrical potential and electric versus the electrical field. As I've illustrated, and I strongly encourage you to do that, go through these graphical illustrations of a positive and negative charge, of a dipole, namely a positive charge and a negative charge, of the electrical field, characterizing so that charged object in terms of a vector field mathematically, namely specifically now here the electrical field, but in a completely equivalent description mathematically is not to characterize that charge or charge distribution to that effect by a vector field, an electric field, but by a scalar function, namely the so-called electric potential V. And there's an extremely profound and well-defined connection between both, which I will remind you now as we move along. Now, if you're moving with the direction of the electrical field, means that you're moving in the direction of decreasing potential and vice versa. And I always want you to develop your intuition by the analogy of a gravitational field restricted to the Earth's surface. So now, what did I just say? If you're moving with the direction of the electrical field, means you're moving in the direction of decreasing electrical potential. The analogy now to a gravitational field restricted to the Earth's surface would be, imagine you're standing somewhere on ground and you're holding a ball in your hand, okay? And you let that ball now drop down from you holding it in your hand down to the ground. Then this ball is moving in the direction of the actual gravitational field, which is downward. But you're moving in the direction of decreasing potential energy. Because if you lift it up, then you are increasing the potential energy. And remember the notion, we're dividing out the mass, come to the gravitational potential, or going from the gravitational force to the gravitational field. The pendant now concerning electrical phenomena, we're going for the Coulomb force divided by the charge to the electrical field, and from the electrical potential energy dividing out the charge, we come to the electrical potential. So again, moving with the direction of the electrical field means moving in the direction of decreasing electric potential and vice versa. Now, to move a unit charge slowly against the electrical force, we must apply an external force per unit charge equal and opposite to the electrical force per unit charge. The electrical force per unit charge by itself is the electrical field. That is that whole notion of going from the Coulomb force, dividing out the charge, come to the electrical field. And to remind you of the deep connection now between not potential energy and force, but between potential and the electrical field, where we divided out the charge, is now written below. The change in the electrical potential is the potential, the electric potential at the final state, minus the electrical potential in the initial state. Same thing, but multiplying by the charge, you would have here delta U for the potential energy, U of F minus U of I, equals to, well, for the potential energy, we would have had on the right-hand side minus the actual work. So the integral over force times displacement. Now here we divide out the charge. So we therefore have a line integral from the initial to the final configuration and line integral of the electrical field along an infinitesimal path element dl. And the unit of the electrical field can be expressed as 1 Newton per Coulomb, which is clear. You take the electrical force, you divide out the charge, so therefore it's Newton per Coulomb. Or you can also express this as volt per meter. All right, so a couple of more things now on the connection between potential energy and electrical potential, because this is really new, that notion. As I mentioned to you on Monday and already last week, we did not talk so much for gravitational fields about the notion dividing out the mass. Now, when a particle with charge q moves from a point where the potential is VI, electrical potential, to a point where the electrical potential is VF, the change in the potential energy is simply then multiplying it by the charge, because the electrical potential is potential energy per unit charge. And now there is a very special unit that you introduce if you're considering a charge equals to the magnitude of the electron charge. The electron charge is 1.602 times 10 to the minus 19 Coulomb. And imagine you would move such an amount of charge of the electron charge with regard to an electrical potential difference of 1 volt. So imagine this delta V amount would be 1 volt. Then the change in energy is defined as 1 electron volt. Namely, you have here the unit charge, you have 1 volt difference, then this would be 1.602 times 10 to the minus 19, but joule now. Coulomb times volt. So Coulomb times volt refers to joule. Okay, so now let me remind you of the deep and important connection between characterizing a charged object in terms of a vector field or a scalar field. So what I show you here is again a positive charge, setting up, modifying space around it in terms of an electrical field. The electrical field lines are pointing away from that positive charge, radially outward. There's only a radial dependence, there's no polar angle, and there's no azimuthal angle dependence. So it's perfectly spherically symmetric. Now, instead of characterizing now the electrical field, the charge by an electrical field, so a vector field, we can also now consider the respective electrical potential. And what I show you here is now a graphical illustration of locations, and you have to imagine this is now a cross-sectional view. In 3 dimensions, of course, the electrical field points radially outward in all of the radial directions. So you see here now a projection onto the plane. So Leo said this in class when I asked what is the actual geometrical distribution of places where the electrical potential would be a constant. It is a sphere, it's the surface of a sphere. So here now you see circles. So now you see here, for example, one circle in this illustration where the electrical potential would be 30 volts, then you have to 50 volts, and then you have to 70 volts, and so on, 110, 130, and so on. And what you notice here, the difference between these two with these circles for which the potential jump is always 20 volts. It's always the same, but the separation between these rings is getting smaller and smaller. And what does this tell you? Well, delta V over delta R is nothing else than a measure of the underlying electrical field. So meaning the change in the electrical potential as you move in a certain spatial direction, if there's a drastic change, that is an indication that there's a very strong underlying field. This is a very, very profound and important concept. So let me repeat this. If you do encounter a rapid change of a potential, here we're talking about an electric potential. It could be also a magnetic, a gravitational field, the respective potential. And if you do encounter, if you move along a spatial dimension, a rapid change in that electrical potential, then this change is indicative of a force, and if you divide out mass or charge, characterizing then the gravitational field or the electrical field. That's an extremely important concept. And now you can imagine you can move along Cartesian coordinates, radial coordinates, but this is now dependent on what is the underlying symmetry of your field. Here we have a point charge, so the underlying symmetry of the field is characterized by spherical coordinates, specifically actually only the radial coordinate, because the polar angle and azimuthal angle, there is no dependence on the electrical field. So what you now encounter here is the change in the electrical potential over a radial distance, delta R. So delta V over delta R is nothing else than the electrical field up to this minus sign here. Okay? And that minus sign is nothing else than, going back to what I told you before, moving with the direction of the electrical field means moving in the direction of decreasing potential. This is directly related to that. Okay, so now you see here mathematically that formulation, the electrical field is equals to minus the gradient or the Nabla operator acting on the scalar function. If you're only talking about specifically the radial dimensions, then this would be minus dV dr. And always see the analogy to the potential energy of a spring, which is a half kx squared. To get to the respective force would be then minus du dx. So if you're calculating the derivative of a half kx squared, that would be what? K times x. So the restoring force, Hooke's law, is minus kx. Okay? All right, so here I show you another example of a graphic illustration of an electrical field, which is much more complicated now, not just one charge, but two charges. A positive charge on the right and a negative charge on the left here. The electrical field and the respective equipotential lines. Equipotential lines meaning where the electrical potential is identical, meaning going from minus 30 to minus 50 to minus 70 volts and so on. Another thing which I want to point out here, this is a mathematical detail, that field lines and equipotential lines are at every point in space perpendicular to each other. Okay? All right, so here's a positive and a negative charge, a dipole, and here you see two same sign charges, plus plus, the electrical field lines and the respective equipotential lines. All right, and last but not least, I want to show you here now the electrical field of a point charge Q, a positive charge in close connection to a metallic surface here. In this metallic surface here, charges after an equilibrium has been reached, these charge carriers are not moving around anymore. So there is no electrical field parallel to the actual surface here. And therefore, there's no force parallel to the surface, and if there's no force, the respective electrical potential is a constant here. So the surface, a metallic surface, is in fact a equipotential surface. And the electrical field lines, therefore, and this is a general true statement, electrical field lines are perpendicular to equipotential lines. And therefore, specifically, electrical fields enter perpendicular to a metallic surface. All right, so let's come now to capacitors. And let me first dwell a little bit on this graphical illustration, what you have here. You have here a general positive charge distribution plus Q. Let me refer to this as conductor A. And you have here another charge distribution minus Q here. They set up an electrical field in between here, and a configuration like this is what is called a so-called capacitor. Now, when the capacitor is charged, it means the two conductors have charges with equal magnitude and opposite sign. But the net charge, of course, of this whole configuration is always zero. So now let me consider specific geometrical configurations of a general capacitor like this. Namely, what we will encounter now is a planar capacitor, say two infinitely charged plates. We'll then consider a cylindrical capacitor or a spherical capacitor. And there's now one very interesting thing here now is we're taking now that charge and dividing out the potential difference between these two charged objects here. And that ratio, that charge, the magnitude of the charge of each conductor divided by the potential difference between conductors VAB is a constant, and that characterizes that geometrical configuration of that, and that is referred to as the so-called capacitance. And the unit of capacitance is therefore can be easily derived as charge over electrical potential is therefore 1 coulomb per volt, and that is referred to as 1 Farad in honor of Michael Faraday, who was a very important physicist in the 19th century. He was born in 1791 and lived until 1867. There's in fact one of the three Maxwell's equation is actually referred to him in honor of him, the so-called Faraday law, which we'll come to in a couple of weeks. So 1 Farad is 1 coulomb per volt, and then you can rewrite volt, and you can also write this as 1 coulomb square per Newton meter, or 1 coulomb square per joule. And you see here now a commercial realization of capacitors. Capacitors, and I don't want to dwell on this at the moment yet, have an enormous practical application, namely where you have two conductors in a certain geometrical configuration, not with vacuum in between, but with a certain plastic material in between, has a huge practical application. You see here one wire coming here, for example, from the cylindrical capacitor to the left, connected to one conductor, and one wire connected to the other conductor, and they are separated by a certain type of plastic, so-called dielectric material. So let me now discuss in a little bit more general context the first type of geometrical configuration of two conductors, the so-called parallel plate capacitor. So you see here on the left-hand side, imagine this is an infinitely large plate here. We know therefore what type of field we are getting in between. When I say infinitely large, this is how we're solving this problem. But here I show you a plate of side length A, area A, so area would be A squared. On the top plate you have charge plus Q, on the bottom plate you have the charge minus Q. They set up a potential difference VAB. They're both connected to a wire, and these two plates are separated by the distance D here. Now, you see here now on the right hand side the type of electrical field. You see now that the field is fairly uniform in between here, but then it diverges from a fairly uniform field configuration when you're going on the edges. And now The approximation what we will be doing right now is that we are considering now a field which looks like this here, a perfectly uniform idealized model of the electrical field between two infinitely large charge plates here. Okay, and in fact we applied Gauss's law to calculate that electrical field. And I will not solve this right now again, but I strongly encourage you to go and calculate the electrical field applying Gauss's law. We did this first separately for one infinitely large plate, and we came to a value of a half sigma divided by epsilon naught. Sigma is the charge density, charge per unit area. And we received also for the negatively charged plate a value of a minus a half sigma over epsilon naught. I want you to draw this out for yourself again. So field lines are going from the positive plate outward, and then from the negative plate, view them first separately, entering the negative plate. But now in between they're overlapping each other. Whereas outside of both plates, they cancel each other. And so therefore, in magnitude, you have in between the two infinitely large charged plates a magnitude of sigma divided by epsilon naught. So now I told you, if we're now taking the charge on each of these plates and dividing out the potential difference between the both plates, then we're getting a value which is called the capacitance. Here now the capacitance of a parallel plate capacitor in vacuum. We're not considering yet to stuffing some material in there. Then, and I will derive this quantity right now. We will find that this capacitance for a parallel plate capacitor is epsilon naught, the electrical constant, times the area for each plate divided by the actual distance. So what I want to do now is stop here and actually calculate now the capacitance for a parallel plate capacitor, then for a spherical capacitor, followed by the calculation of a cylindrical capacitor. Please go through this carefully. I expect that you are familiar with this. This is an extremely important part in preparation also for next week. So let me stop here, and then we'll go through the actual calculation. Okay, so let me now first discuss the calculation for various capacitor arrangements. Let's first start with a parallel plate capacitor. And as I said before, I really expect you to review these very basic calculations. So let's first do a parallel plate capacitor. So let's see. Imagine you have here one plate here. Make this a little bit larger. It's connected to a wire. You have here on the bottom another plate also connected to a wire. And let's imagine the top plate has a positive charge, as it is shown here, and the bottom plate has a negative charge. Then you know what type of field configuration we're setting up in between here, right? So now we are imagining that these for simplicity, that these plates are infinitely large. We are ignoring any kind of edge effects, and we have a perfectly uniform electrical field right in between here. Okay. So I'm not going through the calculation of the electrical field applying actually Gauss's law. These two plates here are separated by a distance d here, and each plate has an area a here. All right, so now capacitance is defined as the ratio of charge, the magnitude of charge divided by the potential difference. So now, the charge can be now formulated, this ratio can be now formulated in the following way. Before we continue here, let me first remind you of a couple of things. We calculated already as a function of y as the vertical coordinate the potential energy, and you know the relation between potential energy and electrical potential. The potential energy turned out to be Q times the electrical field times y here. I remind you, this is nothing else than the force times the vertical distance. In complete analogy to what you know from gravitational fields, mg, the force, times the vertical distance. Now, the electrical field is nothing else than the charge density sigma divided by epsilon naught equals to, well, in the charge density per unit area, we can write this as Q divided by the respective area, epsilon naught here. So therefore we have then what? U of y equals to. So let's now replace the electrical field by our description here. So we have now Q times, now we replace the electrical field as capital Q, the charge on each plate, times A times epsilon naught times y. And we're choosing the 0 point here at 0, just like the analogy to a gravitational field restricted to an Earth's surface. U of 0, z equals to 0, equals to 0. So now delta V equals to delta U divided by that test charge small q here. So therefore, what do we have? We have therefore capital Q times y divided by A over epsilon naught. Okay? So now we can go back and say, okay, so now we're evaluating the potential difference for a specific value here. Namely, for the specific value here of y equals to d. So imagine I would draw here a coordinate system. And center it here. Then here at the bottom where the negative plate is, we have y equals to 0. At the top we have here y equals to d. So therefore let's evaluate this potential difference for y equals to d. Then we would have here the charge q divided by q, but now we replace y with d, and then times a epsilon naught. And you see here now the charge cancel out, and we therefore obtain for the capacitance of a parallel plate capacitor the following ratio: A times epsilon naught divided by D. All right, so let me box this important result here now. Okay. All right, so now let's continue here and talk about a spherical capacitor. So what would be a spherical capacitor in terms of the actual practical realization? Instead of having what you have in a parallel plate capacitor, you do your two conductors as two plates, planar objects, metallic plates. You have now, for a spherical capacitor, the two metallic objects carrying the opposite charge of same magnitude, two spherical shells. So two shells of radius RA and RB with, let's say, RB larger than RA. So now the electrical potential, and again, I will not derive this right now, is something that you can easily do for yourself. Imagine I give you a spherical shell and there's a certain amount of charge on that. Apply now Gauss's law. You get to the value what you know from a point charge. So the charge, the actual charge on that, divided by 4 pi epsilon naught times r. So therefore the potential difference delta V is therefore V of RA minus V of RB equals to the charge divided by 4 pi epsilon naught RA minus Q divided by 4 pi epsilon, 4 pi epsilon naught RB. And you see RB is larger than RA, so therefore the second term will be therefore smaller than the first term. So this will be therefore overall positive. So then now we can rewrite this a little bit. The charge Q divided by 4 pi epsilon naught times, and then a geometrical ratio of the radii RB minus RA divided by the common denominator, which is here RA times RB. And therefore the capacitance is then easily obtained. So the ratio Q divided by delta V equals to, so now we have the charge Q divided by, so we have now the potential difference, this would be now Q. And then we have in the numerator also here RB minus RA. And then in the denominator we have 4 pi epsilon naught RA times RB. So therefore we have the charge cancel out, and therefore we're left with an entire quantity which is entirely determined by the geometrical configuration for this spherical capacitor arrangement. So RB minus RA. So let me also box here this result. So the capacitor Q for a spherical capacitor is therefore 4 pi epsilon naught RB divided by the difference in the radii. So let me also box this here. And then we come to the last example, namely a cylindrical capacitor. Okay, all right. So now last case, third, is now a cylindrical. Okay. So let me spend a little bit more time here and as an example to actually determine, because that I have not done so much in all detail, not the electrical field, we have done that, but determine for the electrical potential from the electrical field. Let's see. So for a cylindrical symmetric electrical field, and that's what we're talking about here. So the capacitor arrangement would be here now, two cylindrical shells with, and I'm characterizing them with an inner radius for the one shell, metallic shell, and R out. Whereas obviously R out is larger than Rn. Okay? All right, so now let's first calculate the electrical field. So what's the idea here? Well, the idea would be here, well, we apply Gauss's law E dA equals to 1 over epsilon naught times the enclosed charge. So now, let me make a sketch here. So you have here one cylindrical shell. Here would be the center. And here would be the other side. Okay? And so let's imagine we have here the arrangement would be here relative measured relative from the center here. This is the radius r here. And there's a certain uniform charge density on that here. So I characterize the amount of charge as a certain total charge Q here, but imagine this here has a certain length here, L. So therefore I can formulate a linear charge density as capital Q divided by L. All right, so now you set up a cylindrical field here and the aerial unit vector, and you surround this now by a Gaussian surface, closed surface all around here. And determine then the flux, the total flux through that. So you have the cylindrical shell in between and the two end caps. And the two end caps, you have no contribution here because dA and the electric field would be perpendicular, and you only have a contribution in between here. So this would therefore, at the end of the day, at a fixed radius E would be E times now the area of the cylindrical shell, which is 2 pi r times L equals to 1 over epsilon naught times, and now what is the enclosed charge? The enclosed charge would be therefore lambda times L. And so therefore the electrical field E of R is therefore nothing else than lambda divided by 2 pi epsilon naught times R. Okay? All right, so let's box this here too, since this is an important result, which we're now using to calculate the potential difference between two cylindrical shells. Okay. So for the potential then, what do we now have? So we have delta V of R is therefore minus the electrical field E dr. Okay, so now the electrical field has only is only dependent on R, so vectorial in the radial unit vector direction. So E is therefore E of R times the radial unit vector, and dr is dr times the radial unit vector. So this is something very simple. We end up then with a product of the magnitude of the electrical field times dr, and have an integral from the inner to the outer radius. So what do we end up here then with? Minus. So now there are lots of constants for the electrical field. So we have lambda divided by 2 pi epsilon naught. Then we have an integral from the inner radius, r in, to r out, 1 over the radius 1 over r dr. And you know what the integral is of 1 over r. This is the natural log. So then you would have here natural log of r out minus r in. You can change the order of that, write this as a ratio, and then you can reflect this with a change of the minus sign. So overall get then here lambda divided by 2 pi epsilon naught times the natural log of r in divided by r out. All right, so delta V is therefore lambda divided by 2 pi epsilon naught times the natural log of Rn divided by R out. Okay? All right, so let me also box this, and then we're almost done. So, and now we just calculate now the ratio to evaluate the capacitance. Namely, capacitance is now Q divided by delta V equals to, so the charge is now lambda, the linear charge density times L divided by, and delta V is now what? Delta V would be here now lambda. The other constants are 2 pi epsilon naught. And then you have here the natural log of Rn divided by R out. And you see here, you can simplify this. Lambda lambda cancels out. And you end up here with, therefore, the following quantity for characterizing a cylindrical capacitor, namely 2 pi epsilon naught times L divided by the natural log of Rn divided by R out. And let's box this here as well. Okay, all right, so let's go back here. So we have now calculated the capacitance, the ratio of the charge divided by the respective electrical potential difference for 3 geometrical configurations of conductors. One for a parallel plate capacitor, and you see here that capacitor value entirely depends on only for those specific geometrical quantities, area, d, the separation, and epsilon naught. Then we went through a spherical capacitor. Again, you have the dependency of epsilon naught, but now the dependency on the inner and outer radius of this of these spherical shells. And last but not least, we evaluated now the capacitance for a cylindrical arrangement. Depends on epsilon naught, but now the length and the inner and outer radius. Okay, all right, so let me stop here, and then we are continuing now the discussion for the dielectric material and energy inside of a capacitor. Now let me discuss here, and then I will calculate this, the actual energy stored in a capacitor. And this is in a very, very important realization that there's a physical reality. I cannot overemphasize for that there's a physical reality of a field. So let me go back to an illustration, in fact, here. I mean, this is now a detail that we actually considered an idealized model of the field set up between 2 charged plates. In the reality, we use the right size rather than the realistic drawing. This is a detail. What I want to tell you right now before we calculate this, and it's a very, very important learning step, that the field itself has a physical reality. What do I mean with that? What I mean with that, you have the notion of a new force generated by an electric charge. It modifies space around that charged object, here distributed over plates. And another charge, if you go into that field of that charged plate, experiencing a force. Compared to now the situation of you bringing a test charge there in that space, but that infinitely large place wouldn't be there. Then that test charge would not experiencing a force. So that the field by itself, set up by that infinitely large plate, has a physical reality. It comes into existence, and you know something about that if you bring a test charge to that. Not only does it have an impact on a charge in terms of a force, namely a test charge, it also stores energy. Okay, so that's a very, very important thing now, that a field by itself stores energy. Okay, and this is what I actually want to calculate now. So first I want to show you this and then go through the actual calculation. The potential energy stored in a capacitor is Q squared divided by 2C. We'll go through this calculation. You can write this also as a half C, the capacitor times the potential difference, or half QV. This is only a matter of replacing now the capacitance by Q divided by the potential difference. And the capacitor energy is stored in the electrical field between the plates. If you now take this potential energy of a parallel plate capacitor, for example, and divide out the volume, so what would be the volume between a parallel plate capacitor? Well, the volume would be, well, you know the separation D and the area, so it's A times D. So if I literally take the potential energy and divide it out by the volume, so then come to a quantity which is referred to as energy density in vacuum, then this energy density, which I will calculate now for you, is a half epsilon naught, simply a constant, times the electrical field squared. So the electrical field squared, the square of the electrical field, up to units, up to multiplying this by epsilon naught, but that's a detail. That's what I want you to realize. The field squared is a measure of the energy density. And in a couple of weeks, when we're talking about magnetic fields, then we're not talking about an electrical field here, but a new type of field with new characteristics. The symbol for that will be B. And we will also calculate then an energy density for a magnetic field will also go like B squared. So the field squared is a measure of energy density. So let me stop here and calculate this. Okay, so what I will do now is calculating the potential energy for a capacitor. All right, so first part will be energy of a capacitor. All right, so the capacitor again is the ratio of the charge divided by the electrical potential. So now the total potential energy, if you have a variation of the potential energy, would be from 0 to the total charge du. And du equals to the electrical potential times a small charge dq here. So this is where the notion du is coming from. You have a tiny little charge dq here, given an electrical potential, and now you're integrating over the entire charge amount. Then you're evaluating this integral expression here. So let's do this right now. So u equals to the integral from 0 to the total charge is therefore v dq. What is now v? Well, v is the small charge q divided by c. So we have here 1 over the capacitance. So we replace now v by small q over c. Integral from 0 to q dq. And you know how to evaluate this integral. This is 1 over the capacitance, and therefore this is q squared divided by 2 here. So therefore u is nothing else than a half of Q squared over C. So let me box this important result here right now. Okay, so now we can reformulate this a little bit. So with Q equals to C times V, then we're finding U equals to 1 over C times Q squared over 2. This is therefore 1 over C times, so now we're replacing Q by C times V. So that would be now C squared times V squared times that factor 1/2. And now you cancel out one C here, one C here, and then you have here 1/2 CV squared. Or you write this also as replacing now the capacitance by Q over V. You can also write this as 1/2. You write this as Q divided by V times V squared, and then you have here 1/2 times Q times V. Okay? Alright, so here's another important result that I want to box here, namely writing U as 1/2 CV squared, or writing U also as 1/2 QV. Okay? Alright, so let me box these important results here right now. And then we come to this very important calculation of the energy density, which is related to the square of the electrical field. Alright, so let's do this fun calculation now. So this is the energy of the capacitor first, so now the energy density. So small u is now capital U divided by the volume, which is A times D, which is now, well, we calculated this, U equals to 1/2 CV squared divided by AD. So now let me replace now various quantities here. A times D for the volume in the denominator we leave the same. Now, we calculate, and then you have this factor 1/2, I put factor 2 here. We calculate that the capacitor, capacitance for a parallel plate capacitance is epsilon naught times A divided by D. And the electrical potential for a parallel plate capacitor is V equals to ED. So replace this here with E squared times D squared. So now we can simplify this quite a bit here. A cancels out, the 2D cancel out, and you know what? Here you go. You have 1/2 from here, epsilon naught and times the electrical field squared. So that's a very important realization, that the energy density scale is entirely determined by the field squared. Okay. So please go through this simple calculation here concerning the energy of a capacitor. This is generally a statement. This is not nothing specific for a parallel plate or cylindrical or spherical capacitor. And here I calculated the energy density, assuming a configuration for um, the parallel plate capacitor. It simply makes the whole calculation much easier. And what we see here, the energy density is simply a half epsilon naught E squared. But it's a generally true statement that the energy density scales with the square of the electrical field. All right, so let's stop here. Now we're finishing up the discussion about capacitors. And actually, doing something which has enormous practical applications. So far, when I calculated the capacitance value for a parallel plate capacitor, for a cylindrical capacitor or spherical capacitor, I assumed that the space in between the two conductors, irrespective of their geometrical configuration, is in fact vacuum. But we are leaving this ideal world right now and stuffing it with a non-conducting material. Namely, most conductors have a non-conducting material, a so-called dielectric material in between. So keep in mind, I really want to emphasize the notion of a non-conducting material. It's not another metallic material in between. And here you see an example, a sketch for that. For a cylindrical capacitor, you have a conductor, it's one metallic foil, and then you have a dielectric sheet in between, and you roll this up and you come to a cylindrical configuration like that. Now, what happens now if I in fact have a capacitor and I stuff afterwards a dielectric material in between? So imagine I give you two charged plates here, one carrying a charge plus Q, the other minus Q. They're separated by a distance d. There's vacuum, and therefore you measure a certain potential difference. If I'm now inserting a dielectric material in between here, what will happen, since Q is unchanged, the charge will stay there like this, the capacitance is increased with the dielectric material. Why? When we insert an uncharged sheet of dielectric material, such as a glass, paraffin, or polystyrene material between the plates, the potential difference decreases to a smaller value. So now, why can we understand that it decreases to a smaller value? You remember how the actual electric potential varies with the electrical field? How does it vary with the electrical field, the potential difference, the electrical potential? Well, the potential energy is always EQ times D. Now, therefore, dividing out the charge, so therefore V is equals to E times D. So D stays the same, the separation between these two plates. So therefore, if I'm making this statement here that the potential difference decreases, therefore this can only be the case if the electrical field decreases. How can the electrical field now decrease? From a vacuum configuration to a configuration if the dielectric is introduced. Well, and this is what I want to explain to you now. And I will not give you here a full-blown detailed mathematical explanation for them, but only conceptually. So when a dielectric is inserted between the plates of a capacitor, the electric field decreases. And I want to give you a feel for why this is like this. And the reason for that is we're talking about here inserting a dielectric, a non-conducting material. In contrast to a metallic material, charge carriers cannot freely move around. However, these charge carriers, let's in general call them molecules, can change their orientation. And they're aligning themselves, so to say, inside of the external electrical field set up by these two plates here. Now, the overall orientation is now the following. So you have here on the left-hand side a positive plate, right side negative plate. Now you insert the dielectric material. And what you, so to say, have is that molecules orient themselves in a way that their negative side is oriented towards the positive plate, and the positive side is oriented towards the negative plate. What is now the net effect on the overall electric field in between? That's what I want to show you in this flow chart going now from left to right. On the very left-hand side under a node dielectric, you see the overall electric field, bare electric field just in vacuum. Now we're inserting the dielectric material was just inserted. What happens then that molecules orient themselves inside of this external electrical field, where the negative part is positioned or directed towards the positive plate, the positive side towards the negative plate. This sets up by itself an electrical field, which is in the opposite direction to the external electrical field set up by the plates. And now you use the superposition principle. You can answer this for yourself. You see this graphically, that the net resultant field is somewhat smaller. So the resultant field, let's go back here. The resultant field is smaller, the electrical potential is smaller, but the capacitance is overall larger. So now you can tune, depending on the type of material in between here, therefore change that capacitance value. And not only depend on the geometry, but you can tune this over a wide variety of range using different materials. And this is what is summarized here. So the capacitance of a parallel plate capacitor with a dielectric material included can be therefore written as C naught, which is the capacitance in vacuum, which is epsilon naught A over D, times, and we multiply now this modification where we come to a larger capacitance if we insert a dielectric material with a so-called dielectric constant K. And we can include write this as one constant here, epsilon, rather than epsilon naught, as K times epsilon naught here. So the overall capacitance of a parallel plate capacitor with a dielectric material is therefore epsilon, which is K times epsilon naught, times A over D. And K is a material-dependent constant. And I'll give you a table to give you a feel for that for different types of material. And now this notion also translates into the energy density. For in vacuum, we had a half epsilon naught E squared. So now instead of epsilon naught, you have K times epsilon naught. Or we can summarize this to epsilon, which is called the permittivity. K times epsilon naught. All right. So now, what are typical values for this constant K? Well, let's start with vacuum. K is 1. Air is slightly different than 1, 1.00059. And now you have different types of material. Teflon, mylar, glass, glycerin. And you have water here, a liquid dielectric material. Namely, water molecules can beautifully polarize themselves inside of an external electrical field. So this is just to give you some examples for that. Now, if the electrical field is strong enough, a dielectric breakdown occurs and the dielectric becomes a conductor. So what did I say before? A dielectric is a non-conducting material. And normally these charge carriers cannot move around, but they can orient themselves inside of an external electrical field. But if this electrical field is extremely large, then they can start actually to move around and becomes a conductor. And the maximum electrical field for which this occurs is so-called dielectric strength. It's a maximum electric field to characterize this. So, and I give you now an example for this dielectric strength in terms of the maximum electrical field for which a dielectric becomes in fact a conductor for two types of material. A glass material, which has a K value of 4.7, and the dielectric strength is 1 times 10 to the power of 7 volt per meter. So a very, very large electric field. In dry air has a dielectric constant of 3 times 10 to the 6. And here you see one of those examples where a breakthrough actually occurs with a lightning. Normally, air is a perfect conductor, but if the electrical field between the cloud and the Earth is so large, then a breakthrough actually does occur. All right, so now talking about moving charges. So now completely switch gears. We have so far restricted ourselves to the notion that charge carriers remain in place and do not move around. This is the whole field of electrostatics. We characterize point charges, then multiple point charges, discrete charge, and then went to continuous charge distribution, characterize them in terms of their electrical field, and then mathematically equivalent in terms of their electrical potential. What I now want to consider is the idea that these charge carriers, due to an external electrical field, are actually moving. So what I show you here is an electrical field, positive charge carriers with a certain velocity, a so-called drift velocity, giving rise to a certain stream of these charge carriers. And now let me define a new quantity. The current through an area is defined as the ratio of dq dt, so how much charge flows per unit time. Now that charge per unit time can be calculated as follows. So this is how many concentration of moving charges you have. So the units for that is number of charges per unit volume. Okay, charges per unit volume. Now you have here v, the velocity, which has units of meters per second, length per second. Length times area is volume. So you cancel out already the volume here, and then you're left with coulomb per second. So current, instead of writing current as dq dt, you write it here in terms of more explicit quantities, namely the concentration of charge carriers per unit volume, the charge per the particle, the drift velocity, and the actually cross-sectional area. And you can see here, if you leave the drift speed the same, in the concentration of particles in the charge, but you made the area larger, the current is getting larger. Now, what is the unit for the current? The unit for current, this has been adopted from a very famous physicist, French physicist, André-Marie Ampère. He was born in 1775, died in 1836. The ampere is equivalent to 1 coulomb per second. Now, the coulomb is the international unit of the electric charge. It is the charge transported by a constant current of 1 ampere in 1 second. This is how a coulomb is defined. Now, what about actual ampere? I will come to that in a second. Coulomb here, Charles-Auguste de Coulomb, lived from 1736 to 1806. Now, let me make a brief statement about current. Now, the ampere is the current, and let me first read this definition here. The ampere is the current which, if maintained in two straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart. So you have here a wire and here a wire. And there's a current flowing through that, namely charge per unit time, would produce between these two conductors a force of 2 times 10 to minus 7 Newton per meter of length. The force is due to the force by a moving charge inside a circular magnetic field. This we will come to where this force is actually coming about, namely, and we will discuss this after the circuit discussion, a new type of field, magnetic field, namely, given a magnetic field, a moving charge experiencing a force. But we'll come to that. So this is formally the definition of SI definition of ampere. Namely, if you have two conductors, 1 ampere is if you have them placed by 1 meter apart, experience a force relative to each other of 2 times 10 to minus 7 Newton. So let me talk a little bit now about current flow. Generally, I show you here an illustration of a wire of a metallic, let's say copper material, for example, in the direction of an electrical field. And imagine you have here a higher potential to the left and a lower potential to the right here. So setting up an electrical field like that. Then normally what you would clearly see is that electrons would move towards the positive side. So imagine you have here a parallel plate to the right, to the left, positive, then to the right you have a negative plate. That gives rise to the electric field, electric charge, and negative charges would move to the left here. But by convention, current is treated as the flow of positive charge. So you see here the electrical field is directed to the right. The flow of the negative charges is to the left here. The current is defined as relative to the direction of the underlying electrical field of those charge carriers, but of course relative to positive charges. So now there comes a couple of definitions here now. Remember NQVD? So let's go back here, NQVD here, okay? So current is NQVD, the drift velocity times area. If I divide now the area here, the current divided by the area, then I come to a quantity which is so-called current density, which is given by the product of the concentration of charge carriers per unit volume times the charge times the drift velocity. That's what you see here. And the direction of the drift velocity is inherited to the current density direction. So current density is the current per unit area, but written here as NQ times the drift velocity. The current density is always in the same direction as the electrical field, so because the drift velocity is taken as the direction of the electrical field here, as I've showed you here before. But relative, of course, to the respective positive charge carriers. So now imagine you have charge carriers flowing through a wire. They're not flowing without any resistance. There's a lot of stuff in there in a microscopic sense, namely other atoms, where they bounce against each other. And the underlying structure, atomic structure, will determine how easily or how not easily these charge carriers can flow through a metallic material. And to characterize this, you define the following ratio: the magnitude of the electrical field in the material divided by the magnitude of the current density. And that ratio is called the resistivity of a material. And the units of that quantity is 1 volt per ampere. And you also refer to this as 1 ohm. Sorry, 1 ohm meter, whereas 1 ohm is 1 volt per current. And the inverse of this quantity, so if you not take the resistivity but 1 over rho, this is referred to as the conductivity, whereas the conductivity has the units of 1 Siemens per meter, with 1 Siemens is 1 over units of ohm, and ohm is 1 volt per current. This is all derived, these units, in honors of famous physicists who helped in the development of the Georg Simon Ohm and Ernst Werner Siemens were both German physicists. And you see here a lot of these folks did their work at the end of the 18th into 1970s. This was an enormous boost in the development of electricity and magnetism. Georg Simon Ohm lived from 1789 to 1854, and Ernst Werner Siemens lived from 1816 to 1892. And you probably know the name of Siemens, the company. He was the one who actually founded that company. Let me give you now a couple of examples for this resistivity in units of 1 ohm meter for a couple of types of materials at 20 degrees Celsius, of conductors, metallic material, semiconductors, and so-called insulator material. Silver has a very, very small resistivity, 1.6 times 10 to minus 8 in these units, which is quite a bit different than, for example, from lead, or iron. So if you want to deal with material where you have very small resistivity, you better use silver, copper, or gold. Then there's a certain class of materials, so-called semiconductors. There are, in their behavior between conductors and insulators, plays in the development of electronics a very important role, where their conductivity depends drastically on temperature and things like this. So there's a wide range for that. That's why this is quoted like that. Whereas insulator materials, look now, glass, Teflon, wood, have a very, very large value for the resistivity in contrast to conducting materials. The resistance, so if you now take the resistivity and multiply it by the length divided by the area, then you come to a quantity which has really the units of ohms. That rho is the resistivity is a material constant, but the resistance captures then really, as the word said, the resistance to a given electrical current for a given length and for a given area. And the potential across a conductor is given by the famous so-called Ohm's law, where imagine you have a potential difference here between the beginning of a wire and the end of the wire, with a higher potential to the left, the lower potential here to the right here, therefore giving rise to an electrical field from left to right, a current density from left to right, and therefore an overall current from left to right. And imagine I give you now the resistivity, let's say for silver material, rho here. And I tell you, you have silver material of a certain length and certain area, then the overall resistance is then determined by rho times L divided by the area. So therefore you can see, if you're stuck, let's say, with copper wiring, and you want to make the resistance small as possible, but you're dealing with, you have to transport an electric current over a certain length, then you better make sure that your area of these wires have a large cross-sectional area rather than very small diameter wires. Okay, so I want to stop here right now, and we will then now take these bare wires. We take elements which have resistance, which can be tuned. This is the pendant to a capacitor. We've learned today capacitor can be altered, their capacitance value, by putting a dielectric material in between. And now we have three actually important so-called circuit elements. Bare wiring, for which if you do this right, the resistance is extremely small and you can be almost ignored. Then you have elements for which you choose a certain resistance value, where you use a special material in between here, not necessarily only just metallic material, to tune a certain value of a resistance value, or you're using a capacitor. And all of these three elements in circuit, a wire, a resistor, and a capacitor, together with switches, for example, just an on-off switch, provides a very large breadth of practical applications. And it will become exceedingly important that you understand, if I take certain wiring and resistors and capacitor and connect them to a given potential difference, namely a battery, for example. You all know what a battery is, how we can calculate the potential difference over a resistor. So applying very specific rules and laws to circuits. For example, you take two light bulbs and you put them in series, or you take two light bulbs and put them in parallel. Things like this I will discuss next week on Monday in a very systematic way. This is referred to as so-called circuit analysis. That's a lot of fun. And the rules are also derived from a very famous physicist, German physicist, who worked on this in the 19th century, so-called Kirchhoff's rules. So I will discuss this on Monday. But do me one favor, please go through this material, what we discussed today, especially the calculation of capacitance analytically, and then the calculation, this was very brief, of the energy stored, the electrical energy in a capacitor. And then specifically for a parallel plate capacitor, we used that arrangement to calculate the energy density and came to a very important result that energy density scales with the square of the electrical field, actually. All right, so let me stop here.